Hello, everyone. Hi. Thank you for your response. So I will continue to work on the 4-bar mechanism. And so we finish the mobility part. And yeah, just continue with the 4-bar mechanism. So last time we mentioned in the last slides on Monday, we talked about inversion. So inversion is suppose we have a closed chain. So here we use a crank slider as example. Suppose we have a closed chain and we can fix different links and to make the mechanism work in a different way. So I brought a prototype to demo what happens if we fix different links. So usually we use this mechanism and by fixing this rectangular bar, and we usually use this one as input, the small bar as input. In this case, we call this a crank slider. That means we use the crank. Crank means it can make a full rotation motion. And so this one is called crank. And this one is called slider. And we call this crank slider. That means the input is a crank and output is a slider. So in this case, when we apply certain motion, rotational motion into the crank, then this slider is going to move back and forth, right? So we transform the rotational motion into linear motion. That's the purpose of this mechanism. And of course, you can also make it work like an engine. For engine, the force is applied on the slider, and we make the crank rotate. So you know how engine works? There are some chamber here, and it will cause some combustion. The combustion will push this slider down, and so make this crank to do a full rotational motion. So that can drive your car or your vehicle. So either these two ways we fix this big rectangular bar, and we use either this one as input or this one as input. So we transform either rotational motion into linear motion, or we transform linear motion into rotational motion. But we can also make this linkage to work in a different way. So for example, in the second configuration, we fix the slider instead of this big bar. So we can also fix this one, and here maybe I use this one as a driver. And when you work in a very strange way, we don't usually use it in this way. But just another way we can fix any other links and to make this mechanism to work in a different way. I think I'll fix the third part. I'll demo the configuration D. So we can also fix this slender bar. And this time I also use this crank as this short bar as the input, and use this one as the output. And you can see when I fix this slender bar and I drive this short beam, this short bar, the output will also perform certain motion. I don't know how to describe this motion, but maybe you can install a blade here and it can become a chopper or something. Yeah. So it's just with the same closed chain, we can fix different link and to make it become a different mechanism. It just depends on your application. Yeah. So here the inversion just telling us this. For any closed chain, you may not always use this configuration. You can fix other links and to perform different type of motion. Any questions so far? Yeah, and so in the following slides, we'll focus more on the 4-bar linkage. Here, the 4-bar linkage, I mean this type of 4-bar linkage. So four links, there's no slider here. So 4 are joined and 4 beams or 4-bar. There are several configurations for this 4-bar linkage, so we'll discuss them later. And so the very first thing, if we want to assemble a 4-bar linkage, there's one thing we must satisfy. suppose, well, right now we have 4 bar, and we name the shortest link as S, and the longest one as L. And the other two, we call it P and Q. So it just, the length of these two just in between the S and L. So the very first thing, if I want to assemble a 4-bar linkage, I must satisfy this inequality. So the shortest 3 bar, the length, the summation of the length of the 3 shortest bar must be greater than the longest bar. Otherwise, you can assemble this mechanism. Does this make sense? Yeah. If I have a super long bar, I have 3 short beam. Then in this case, I cannot assemble them as a 4-bar linkage, because if I connect this one, this joint, this hole to this joint, this one connect with this one with this one, but this one cannot reach this one. So that's the very first situation we need to satisfy is this equation, this inequality equation. Yeah. Any question about this one? Okay, but even we can assemble a 4-bar linkage like this, there are still different configuration we can do with this. So here there's a gentleman called Graphical. He create an equality to categorize the 4-bar linkage. So he categorized the 4-bar linkage into type 1 and type 2. So in type 1, it says if the shortest link, the length of shortest link plus the longest one is smaller than the remaining 2, then we call this one as a Graphical linkage. This one is a Graphical linkage, and I will show you its property later. So even in this type 1, you also categorize this mechanism into 3 subtypes. The first one is we use the S, the shortest one, as the input. And in this mechanism, we call it a crank rocker. So I use this one to demo. Here I label with blue label. That's one. That means this one is the shortest one. And the pink one is the longest one. Yeah. So in the very top case, we say if I use the shortest one, the S as the input, then this mechanism will work like a crank rocker. So the crank rocker means my input can do a full cycle rotation motion. So in this case, if I rotate this one, yeah, you can see I can do a full cycle rotation on this blue bar, this one with blue label. And it's called crank rocker. So the output, which is this one we call it a rocker because it's swinging. It's not doing a full rotation, it just swing back and forth. So this mechanism, we call it a crank rocker. That means the input is crank and the output is rocker. But right now we are fixing this longest bar. I can use another configuration. I fix this P or Q, not the longest and not the shortest. I fix this one and I also drive this blue one. You can also see the blue one is still doing the full rotational motion. And this output is still doing the swinging. It's still a rocker. So either this way or this way, they are both crank rocker mechanisms. Yeah. So as long as you are using the shortest bar as input, it's a crank rocker. Yeah. Yeah. Oh, first thing you need to satisfy this S plus L is smaller than P plus Q. Then if you use the S as driver as the input, then this mechanism is a crank rocker. And we can also fix other links and to generate another mechanism. So this time I fix this shortest bar, I use this one as a base. So this one is grounded, it's not moving. And I can either use the pink one or this another one as a driver. I just use the one I'm holding as a driver. So you can see if I fix the shortest bar and I drive this one can do a full rotational motion. And the pink one is doing a rotational motion as well. So in this case, we call this mechanism a double crank. Or another name is also called drag link. You can see this term in the textbook, but it's also called double rocker, double crank, because both the input and output can perform a full cycle rotational motion. Yep. You can see this. And there's another case called otherwise. So any other case, you will become a double rocker. So let me try. So if I fix this one, this P or Q, and I use this P or Q as a driver, I cannot do any full rotational motion. Both the input and output, they are just swinging with certain angle, right? So this just belongs to the third case. We call it double rocker because both of them are doing just swinging within certain angles. Yeah. I fix the bottom one and I move this one, or I move this one. They have some limitations, so they cannot perform a full rotational motion. Yeah, so for type 1, we have 3 subcategories. So if we use the shortest one as input, it works like a crank rocker. Use the shortest one as a base, it works like a double crank, or also called a drag link. And any other case belong to the double rocker. And there's another inequality. If an inequality is in this form, so the shortest one plus the longest one is larger than P plus Q, then either one you fix either one, you use either one as input, they will always perform like a double rocker. Yeah. So usually we use this configuration, this type 1. And this one is smaller, this one is greater. Then how if it's equal? How if S plus L equals P plus Q? In this case, we call it Graphical neutral. It's not greater or is neither smaller. And this one, I think in the real application, we never use this configuration. It would lead to some unpredictable behavior. I will show you some example later. Yeah. So it's just what we've done with the model previously. So crank rocker is the input can do a full rotational motion, and the output is doing a swinging motion. So we call this crank rocker. It belongs to type 1 and use the shortest one as input. And the second case is we fix the shortest one, and you can either use this one or the longest one as driver. Then either case, they can do a full rotational motion. And third one is double rocker. So any other cases not belong to the previous 2 cases are double rocker. So double rocker, you can see the input and output, they can only move within a certain range. They cannot perform a full rotational motion. Okay, so we mentioned another case is if the S plus L equals P plus Q. And it's called Graphical neutral. And it's also called transition linkage. And there will be some position when the linkage will lie flat. That means, well, so this one is a Graphical neutral mechanism. You can see the longest one is 3, shortest one is 1. And this P and Q is 1.5 and 2.5. You can see S plus L will equal P plus Q. They'll both equal 4. So at certain position, they will become a flat line, like this case. But when this happens, this mechanism is gonna perform some unpredictable motions. I will try to show you with my toy. Wait a second, I just need to do a setup. I hope, can you see it clearly? Let me try to. Okay. Okay, so I have this small linkage toys. And right now I'm making this configuration. So you can see the white bar, yellow, and blue, and red. Yeah. So the white bar is the shortest one, and yellow one is the longest one. And right now, the length of the white one plus the yellow one will be the same as the blue one plus the red one. So you can see with certain position, they can become a line, right? So previously in another situation, so this one is not going to become a line. I shift one grid of the white one. So this one, yeah, is gonna become flat. It's not going to become flat. No matter how you rotate it. Yeah. So this one is a Graphical mechanism. This one is a Graphical neutral. Back to this one. So what I was going to say is, we mentioned that this mechanism is going to perform some unpredictable behavior. So what does this mean? When they are currently lying like a flat, in a flat line, if I rotate this one, you can see right now the mechanism is, anyway, look like this way. Just remember this. I push it back, I rotate it again, but this time it performs a different way. Did you see the difference? Or I just use this one so you can see side by side. In both cases, right now I fix the red one and I rotate the white bar. And I want to see how the position of a mechanism will go. So in this case, well, it goes in this way. I rotate the white bar in a clockwise direction. So I'll do the same thing for this one. I'll try to hand it here. Okay, not so bad. So remember, I rotate the white one clockwise. So I'm still doing the clockwise motion this time. But this time, these two mechanisms, they perform in different way. You see the difference? Yeah. This one, yeah, the yellow one cross with the red one. But this one, the yellow one is kind of parallel with the red one. Yeah. So for this Graphical neutral mechanism, once you reach this point, the mechanism become a flat line, and then you further drive this mechanism. There are two possible solutions for this mechanism. But this is not good. It makes the mechanism unpredictable. We don't know if it's gonna be this way or this way. Yeah. Either way is possible. Yeah. So it's not well, maybe there are some applications that require this strange behavior, but I think in general application, we don't like in this way. Yeah. Any questions? So since I already installed a camera, I would like to use this to demo something else. So I changed this mechanism back to a regular gray shift linkage. Yeah, I reduced the white bar a little bit. Yeah. So suppose I have a linkage. Well, so right now they are identical. But okay, so here is the thing. Suppose I have a 4-bar linkage, and I know all the length of this 4-bar. Do you think this one is the only possible configuration? So actually, for every 4-bar mechanism, even with the same length. So right now, these two mechanisms, they have the same length, and they are identical, actually. But I can somehow change, without changing the length, I can make the two mechanisms they behave in different way. So you can compare these two. I reduce the exposure. Yeah. So these two, they have exactly the same length for every link. But right now you can see they actually perform in different way. If I fix the yellow one and I use the white one as a driver, you can see right now the position of a red one and a blue one are different in these two cases. Yeah. And do you think if I rotate, I drive this one, I can make this one become this one? Is it possible? No, it's impossible. No matter how I drive it, it's impossible. This one is always running this way. It's never gonna become this one. Yeah. But when you do the math calculation, sometimes with the same length, you may find two solutions. But you need to make sure what's your original mechanism look like. Yeah, only one possible solutions, but later on we will do some mathematics to calculate the position, the velocity of linkages. But just remember, it's possible that you find two solutions, but only one is possible. That depends on how you assemble this mechanism. If you assemble the mechanism in this way, then yeah, it will never reach this configuration. Yeah. But actually, they are not so much different. So right now, you see they look different. And if I rotate this one with this angle, and I flip this one, I know they are the same. But in the real mechanism, you are going to fix the yellow one, so you cannot just randomly flip them. Yeah. But just for your information, once you fix it, this one is not going to become this one. Yeah. You always the case 2 will always be case 2, unless you disassemble it and reassemble it. Yeah. Okay. Any questions? So back to our slides. So back to our slides. So we mentioned the grid shift neutral. When you reach this point, there are two possible solutions. When you further rotate this A star, this shortest bar. Yeah. So two possible configuration. But for a regular grid shift mechanism, we know if it's this configuration, it's going to stay with it forever. But in the grid shift neutral, once you reach this point, well, it can either switch to this one or switch to this one. Yeah. Okay. So in the previous example, we always fix. Maybe I fix this longest bar and I use the shortest one as driver and to drive this mechanism, and maybe consider this one as output. But in certain application, we may not want to use the mechanism in this way. Sometimes we want to use the coupler. We want to apply the force or apply the actuator on the coupler. What I mean is, if I fix this one, I hold this bar. The coupler driven means we put an actuator on this coupler. Right now, this blue one is a coupler. It's not attached to the ground. So yeah. So the coupler is the link that's not attaching to the ground link. So this one and this one, they are not coupler. Only this one is coupler. Sometimes we want to directly apply the actuator or the actuation, the force on the coupler, rather than in the bar attached to the ground. But it's a very special case. So here what's saying is, we may, sometimes we apply the actuator on the coupler, and the linkage, well, it can be either type 1 double rocker or drag link mechanism. Depends on your application. Well, this description is actually not always true. It can also be crank rocker. Well, just depends on your application. And so I think it's easier for us to take a look of an example first. So one of the example I think about is knee joint. We know our knee is not like a pure R joint. It's not only doing rotation. Or my wrist. It's not just do a pure rotation. It's somehow sliding a little bit between the bones. So some guys, I don't know who, some guys just find it's, in order to mimic the motion of knee, use a 4-bar instead, use a 4-bar mechanism to mimic the motion of knee instead of just a pure R joint. So I just find this video on YouTube. I think you can clearly see its motion. So it's basically an artificial knee. And right now it's driving the coupler. So this part is fixed, and this bar and this bar attached to the ground beam. And we are applying force on this coupler. And by using this mechanism, well, we can make it act more like a real knee. Yeah. It's not doing a pure rotation. It's somehow also doing a sliding and rotational motion together. So another video is showing this type of mechanism, how it's used in an artificial knee. We don't need the music. Yeah, so there's a company, it just built this, this mechanism to help some disability. It's not HD video, so it's not quite clear. But you can see her motion is quite smooth when she's using this mechanism to replace the knee. Yeah. If you use an R joint, it may not be so smooth because the R joint is not working like a real knee. But this one, they tune the length of the 4-bar linkage and try to make the motion more like a real knee. Anyway, if you search a 4-bar knee joint, you can find a lot of video like this. And here I just show you 2 examples. So there's one example that we are using a coupler-driven 4-bar mechanism instead of a regular crank rocker or drag link double rocker mechanism. Yeah. So it depends on your application. Sometimes you may want to use a crank rocker to transform a full rotational motion into a swinging motions. And sometimes you may want to use like an artificial knee and to perform certain motions. So any questions so far? Can you think of any application that using the crank rocker mechanism? So why do we want to use a crank rocker? Because what type of actuator will use in this mechanism? So if I want to drive this one, I'm not going to use my hand to drive it. I may install an actuator to drive this mechanism. Then what type of driver I can use to drive this mechanism? Should be a motor, right? I'll install a motor, fix on this ground link and attach to this shortest link. And so I can make this one move in this way and this one swinging. So have you seen any mechanism that works in this way is swinging, it's not doing rotational motion in your real life application? I think quite often you see the rain scrubber雨刷on your vehicle. It's not doing a rotational motion. It's just a swinging maybe 160 degree. Yeah. But what's the mechanism behind? What's the actuator behind the rain scrubber? It should be a motor, but a motor is doing a full rotational motion. So we need certain mechanism to convert the full rotational motion into like this rocker motion or swinging motion. So in that case, we can use a 4-bar mechanism to perform this type of motion. Yeah. But you may think, well, I can just use a servo motor. Servo motor, I can control the position precisely and also make the rain scrubber to move in this way. But why don't we just use a servo motor? We want to use a mechanism and with a motor to perform the motion of a rain scrubber. Why don't we just use a servo motor? Because servo motor is expensive. So we don't want to install it everywhere. We just want to attach a regular motor, or maybe you just attach some connection from your engine to this linkage. Then you can drive your Rainscooper instead of attach another additional motor. And they will cost you more to buy your vehicle. Yeah. So sometimes it's not because motor cannot achieve this motion. It's because if we use this mechanism, well, it's easier. And we don't need to control the motion. We just make sure the motor is running, it's doing full rotational motion. Then this mechanism, well, we can always do a swinging motion. Yeah. Of course, you can use a servo motor to replace the regular motor, but it's usually not a better option because it's more expensive. And the motion of this Rainscooper is simple, so you don't want to install an expensive device on your vehicle. Okay, so another commonly used 4-bar mechanism is a crank slider. I also call it 4-bar mechanism, but generally, if you heard 4-bar mechanism, is I think 90% of the time they mean this one, not this slider crank. But here I also consider it as a 4-bar mechanism because it also has one ground bar and this bar A, bar B, and bar C. It also has 4 bars, so I think it also belongs to a 4-bar mechanism. So for a crank slider, we usually want, or slider crank, either way. Depends on you use a slider as input or crank as input. If I use a crank as input, I call it crank slider. So for a slider crank or crank slider, usually we want this bar attached to the ground. We want this bar to do a full rotational motion. But in order to perform full rotational motion, you need to make sure these two inequalities are satisfied. So the B must be larger than A, and B minus A must be larger than C. Yeah. You can try to assemble this a mechanism that's not satisfying this inequality. You will find the mechanism was stuck at somewhere, and it's not going to go furthermore. It cannot do a full rotational motion. But here, I don't have an example to show you. Any questions? Maybe I can try to draw it. So suppose B is larger than A. No, suppose B is smaller than A. Then I suppose the crank is not going to be a crank. It's not going to do a full rotational motion. If I draw a mechanism A, if a mechanism looks like this, right now I make the A larger than B, so it's different from the condition we wrote here. So for this one, the bar A is not going to do a full rotational motion. You can imagine if I keep make this white bar rotating counterclockwise direction, it will reach this point. And once you reach this point, wait, you need to go further. Sorry, it's a bit messy here. Once it go further, you will reach a certain point. Then it can no longer move anymore. It cannot move anymore. You will just reach at that point, and you will just stuck there and cannot do further rotational motion. So to ensure your crank slider or slider crank to perform a rotational motion, we must satisfy these two inequalities. Any questions so far?
I have one here.
Yes, please.
Can we see the image?
Sure.
Is the difference between B and A
Yes,
the same as C?
the same as C.
Can it still work?
If B and A, yeah, I think if it's equal, it's just marginally work. So if it's equal, so that's the case when A minus B equals C. I think that's the margin. So yeah, maybe we can put a equal sign here. Yeah. Yeah, I think equal can work, but it's just marginally work. You need to make sure your manufacturing is very precise. Yeah. Any other questions? Okay, so let's move to another chapter. So the content we covered so far belong to the chapter 1 in your textbook. So if you would like to read your textbook. And I will also post some assignment for you to practice. You don't need to submit the assignment. It's just for your own practice. Yeah. So we're going to spend a lot of time on the graphical analysis. So for mechanism, yeah, in chapter 1, we talk about the mobility. So, yes?
回到刚刚那个，
好，没关系。
就是如果那样就变成 A 比 B 长，就是如果 A 板上那个，
这一个，对，这个是 A 比 B 长。哦，你是说如果 A 比 B 短的？Yeah, he's saying I'm drawing this one with a super long A. Yeah, if A is shorter, yeah, I should draw in this way. Yeah, so this one is B minus A equals C. A, B, C.
所以那个 C 不用一定要
往下也可以。B minus A. Yeah, in this case, B is greater than A, but B minus A equals C. Another case, if B minus A. Yeah, here we always consider this C as positive. So it's either going down or going up, we consider. Yeah, it's only positive value. We don't consider direction. So either it's pointing up or pointing down, it's a positive value. Only consider the absolute value. So as I mentioned, we'll spend a lot of time on graphical analysis. So I separate them into part 1 and part 2. So it's we go with part 1 first. Part 1 is easier, yeah, and part 2 is more advanced. And so for graphical analysis, what are we going to analyze? What exactly are we going to analyze? So in this course mechanism, we are going to perform kinematic analysis. So what's kinematic? What does kinematic mean? So kinematic means the analysis that's related to the motion. So the motion includes position and velocity and acceleration. Yeah, so just for your information, we always need to perform the position analysis first because we need to know the current position of a mechanism. And then we can further perform the velocity analysis. And once we know the velocity result, then we can further perform the acceleration analysis. We need to perform them step by step. Yeah, you need to know the position first, then you can do the velocity. Then you know the velocity and position, then you can do the acceleration analysis. So you need to perform them step by step. So let's first take a look of a position analysis of a 4-bar linkage. Suppose I have a 4-bar mechanism look like this. So once this mechanism is settled, the length of all the links, they are known. And right now, the input is at a certain angle. If I want to know, or if I change the input angle a little bit, then how are we going to find the position of this 4-bar mechanism? Yeah. So here's the question. So we know the length of links, all the lengths of links are known, and we just want to apply a random angle for this input, and then we want to determine the position of this 4-bar. How can we do it? So suppose I change the input angle a little bit, then can I find the position of a rest 2-bar? How can we find it? Because we already know the length of the 2 links, so we can use a pair of compass. 我们用圆规. So you can draw an arc. Yeah, I know the length of this bar is gonna, this point is going to rotate at the arc, somewhere on the arc. So I just use a pair of compass and to draw an arc, and I don't know where it is, but I know it's somewhere here. And I also know the length of this output link. So I also use a pair of compass and to draw an arc. And yeah, you just use this as a center and to draw the arc. And the intersection of the blue one and the green one, that will be the location of the joint. Yeah. So by doing so, you can find the mechanism. Once you move the input link with a certain angle, then the position of mechanism would be in this way. Any questions? Okay, let's take a break. Hello. All right, so let's continue. So for this 4-bar mechanism, I think it's fairly simple to do the position analysis. And here we try another example. We try a 5-bar linkage. So this one is going to have 5 bar. To define the position of 5 bar linkage is actually very similar to a 4 bar mechanism. So suppose we know all the lengths of links. I haven't drawn it, but suppose we know. And how many degree, what's the mobility of 5 bar linkage? Let's calculate it first. To remember the, so let's first 5 bar linkage, I mean this type of 5 bar. So there's a ground bar, bar 2, 3, 4, 5. What's the mobility of this one? So use the mobility equation, m minus j minus 1 plus summation I from 1 to j f. So right now we have 5 links, so 3 times 3 minus, how many joints do we have? 5, right? 1, 2, 3, 4, 5. Sorry, n is 5. 5 minus 5 minus 1. And we need to plus the connectivity back. So they are all R joints, so each joint contains 1 connectivity. So we plus 5 back. So 3, 5 minus 5, 0, so minus 1. So minus 3 plus 5, we'll get 2. So mobility of this mechanism is 2. So what does 2 mean? So that means we need to define 2 angles or 2 position variable in order to define the position of a mechanism. So in the 4 bar mechanism, we only need to define 1. So in the previous example, we only define the angle of the link 2 first. Then we can find out the corresponding position. But for this 5 bar, we need to define 2. So I need to define this theta 2, the angle of this bar, and the angle of this bar. If I define theta 2 and theta 5, then the position of this linkage should be able to find. We should be able to find the position of the linkage. So here we just first assume the bar phi is in this location and bar 2 in this location. And how are we going to find the other 2 bar, the position of the other 2? So it's the same as the 4 bar case. You just use a compass, a pair of compass, to draw. If you know the length, you just draw an arc. I didn't draw in the slides, so I just draw it by my hand. So you'll find if you know the length of bar 3, you can use this point as a center and to draw an arc. And use this one as a center to draw an arc. Then once you find an intersection, then that's the position of a joint. So you just connect this point to the other 2 joints. Then you can find the position of this 5 bar linkage. It's the same as a 4 bar case, but the only difference is we need to define 2 angles first. And here I define a theta 2 and theta 5 first. Another case, so a crank slider. So we still want to we also do a position analysis of a crank slider. So the same, we assume all the lengths of the links are known. So the length of this bar, and the offset of this slider is known. And we also change the angle a little bit and to see if we can determine the position of this mechanism. So suppose I rotate the input bar by certain degree in a counterclockwise direction. And how can we find the position of the rest? How can I find the position of a slider and the position of this bar? I know if I already know the length of this bar, I can do the same thing. I just use a pair of compass and to draw the arc. And yeah, the radius of this arc is the same as the length of this bar. Then what should we do next? Any idea? Draw a flat line, right? Because we know the slider is sliding on this surface, so we can draw a line here. We try to find the location of this joint. So I know this joint is gonna move back and forth, but it's always on this line. So I can draw a line here. The trajectory of this joint must lie on this straight line. So I know the joint must be on this green one and also must be on the blue one. So it's gonna be the intersection of these two, the curve and this line. So this is gonna be the new location of a joint. So you just connect them together and just to draw the slider. So this is gonna be the new position of this crank slider mechanism. Any questions? So that's position analysis. So just remember, usually we'll provide you an input, and the mechanism is either a bar, the links is either a bar or a slider. So for slider, you just need to remember slider is always sliding along a line or a curve. And the length of links are always known, so you can use the length of the link to draw an arc. And try to draw the lines and find their intersection, then you can find the position of a mechanism. So next, we are going to move to the velocity analysis. So we'll spend a lot of time on velocity analysis. Position, I think, is fairly simple. It basically is very intuitive. You just, once you have a tool, I think it's easy for you to draw to perform the position analysis. So then we'll perform the velocity analysis. But first, we want to know why are we doing velocity analysis? The velocity analysis is helping us to determine the velocity of a linkage. So for example, this 4-bar mechanism, I just random draw one. Usually, one example is, suppose I drive this bar with certain velocity, I call it omega 2, constant velocity. But I may want to know the velocity of this output. Yeah, so for example, a wrench screwbar. A wrench screwbar, you may want to control the velocity of the screwbar. You don't want it to run too fast or too slow. So you may design the length of this linkage and to make this bar and to swing with your desired velocity, angular velocity. So in order to know the velocity omega 4, we need to perform velocity analysis. And yeah, so that's the purpose of velocity analysis. But very first thing we need to do, as we mentioned before, we need to perform the position analysis first. Then we can further perform the velocity analysis. Yeah, because, for example, for this mechanism, if I put a constant omega 2 here, and maybe the mechanism will further move here. Suppose the omega 2 is constant, so input is constant. Do you think the omega 4 is gonna be constant, or is it gonna vary? How do you think? Usually, the omega 4 won't be a constant if the omega 2 is constant. It depends on your mechanism, but most of the case, it's not going to be a constant. In some very extreme case, well, they might be the same, but most of the case, if the omega 2 is a constant angular acceleration or angular velocity, this one is not going to be constant. And if it's not constant, that means once the angle change, we need to recalculate the velocity again in order to obtain the velocity at this moment. So you need to perform, if you want to find the velocity for a full cycle motion, then you need to divide them into multiple steps. And you need to calculate at this position, you apply this omega 2 and you find the omega 4 at this moment, at this white moment. And later on, you move to this angle with the same angular velocity. You'll find another omega 4 at this moment. Yeah. Okay, so before we perform a mechanism, the velocity analysis of mechanism, let's just review some concept. I think it's a review, it's not a new thing. So let's see the difference between absolute, I didn't put an absolute, absolute position and relative position. So suppose we have a link with point A and point B. It's a rich body. The link is a rich body. So it's not compressible and it's not stretchable. And suppose we have this link. And this link we put on a global coordinate. We call this coordinate, we label it as capital X and capital Y. So to define the position of this point A, we can use a vector to represent the position of point A. We can use a vector connecting from the origin to this A, and there's a vector called RA. We can represent this point A, the position of point A by RA. And this RA is the absolute position corresponding to this coordinate. And for point B, yeah, we can also draw an arrow from the origin to point B. And we can call it as RB. So this RB is representing the position of point B. Yeah. So these two, because right now we are on this XY coordinate, so we call these two the absolute coordinate, absolute position. It's RA and RB. But we want to define another thing. We want to define the relative position of B to A. I don't care about the absolute coordinate. I just want to know what's the relative position of B to A. So in this case, we represent this relative position by using this, this symbol. We call it RB/A. So when you see this symbol, this B/A or something slash something, that means B relative to A. So that means we temporarily consider A as the origin. Yeah. So this arrow is pointing from the origin to point B. Yeah. And we call this RBA. So we use the symbol or representation RBA to represent the position of B relative to A. In other words, we can see from this picture, RBA, they are all vector. RBA is a vector, and RBI, they are all vector. So you can see from this triangle, RBA will be equal to the RB minus RA. Or in other words, RB equals RB. This one equals RA plus RBA. So this absolute velocity of B equals relative position, absolute position of B equals relative position of B to A plus absolute position of A. So we can represent them in this way, the relationship between these three vectors, they are in this form. Any question about this one? And actually RBA, you can also call it RB slash O. O is the origin. So in the following content, we are going to use this RBA or R something slash something a lot. Yeah, so just when you see this, you just remember it means a relative position or velocity or acceleration between 2 points. Any question about this one? So it's just a review of absolute position and relative position. And because right now we want to do velocity analysis. So what's the meaning of velocity? Velocity is actually the rate of change of position with respect of time, or is basically a time derivative. Velocity is time derivative of position. So 2 types of velocity we are going to discuss in the mechanism. One is the angular velocity, and it can be represented in this way. Omega is the angular velocity. It will equal the theta. Theta is the angular position, and over dt. And we'll also consider linear velocity. So I think you all are very familiar with this. So V equals the R. R is the position, and d over dt. And in the previous page, I just write it here. So remember in the previous page, we say RB equals RA plus RBA. So if you do the time derivative of this equation, it will become this one. So we know the velocity, the relationship between the velocity, it can be written as VB equals VA plus the RBA over dt. Well, it looks simple, but the problem is, the question here is, what exactly is this term? Even we know the expression of this one, but when we perform a calculation, what exactly is this one? How are we going to obtain this value? Any questions so far? No? Okay, so remember we said this link is a rich body. So that means the point A, the distance between point A and B will never change. It's fixed. Yeah, so it's not compressible, it's not stretchable. So assume there's a very small increment. So it's a very small time, and this link somehow move a little bit. So just remember here we consider the case. The length of RBA is fixed. It's not changeable. But in the second part of the velocity analysis, we'll consider the RBA is changeable. We'll see that later. So right now we just for this link rich body, the RBA, the length of RBA is fixed. The orientation may change, but the length is fixed. Yeah. So suppose with a very small increment of time, the barge move a little bit. So it moved from this gray position to this white position. And because right now we only consider the relative displacement, so we just assume, or right now we see the problem is we see this A as the origin. So this BA is rotating about the origin. In the real case, if you see it globally, well, this bar may somehow move in the XY coordinate. But right now we are considering the relative displacement and relative velocity. So here we just see this problem as A is fixed and B is rotating. But in the real mechanism, it may like move anywhere along the XY plane. Yeah. So when we see this this small increment, suppose it's rotating with a very small angle, delta theta. And we can represent what then if it's rotating by this delta theta, the angle delta theta, then what's the position, the change of position gonna be look like? So if it's rotating with delta theta, we know the radius is RBA. So I know the displacement of this point will be RBA times delta theta. So delta RBA is a relative displacement with very small increment, or equals RBA times delta theta. Or basically it's R times theta equals to the length. And we know that delta theta can be represented in this way. Theta is omega times the time. And right now it's a very small increment, so we represent as delta t. The delta theta equals omega delta t. So I can rewrite the first equation into this form. The delta RBA equals RBA times omega times delta t. Yeah, and I just put the delta t to the left-hand side. So it's delta RBA over delta t equals RBA times omega. Any questions so far? So therefore, because the delta is very small increment, so we can consider this one as differentiation. So I just assume the delta t is extremely small and it's approaching 0, so you can rewrite this, represent this term in terms of the RBA over dt. Yeah. So that's the absolute value of the RBA over dt. But because it's a vector, so it has direction. But what's the direction of this one? The direction from this figure we know is pointing from this point to this point. So it's as the direction of this arrow. So how can we represent? So right now it's a scalar. It's scalar, so we may want to represent in a vector form. Move it. Now, because it's a vector and I want to represent in a vector, so you can represent this vector as omega cross RBA. What does this omega cross RBA mean? Omega, right now it's counterclockwise. So omega is in this, pointing out of this screen, right? And R is this direction. So omega cross R is this one cross this one. So it's in this, if you do the cross, it's in this direction. So it's pointing this way. So we know, it's so short. We know this one is pointing to the left down direction. Yeah. So we just try to use a vector representation to help us to indicate the direction of a vector, of this new vector. Yeah. We know this one is pointing this way, so we try to create this relationship. So omega cross RBA will also point in the same direction. So yeah, it can be represented this way. So yeah, this one is a vector, just for your information. All the bold fonts are vector. Yeah, I didn't put a vector sign on top of it. But here if I write it this way, then it's a scalar. If I make it bold, then it means a vector. So if you see a bold font on the slides, yeah, that means it's a vector. Any questions? So back to the equation we found in the previous page. Previously, we found the VB is a vector. VB equals VA plus the RBA over DT. But right now for this link, this rich body link, we can represent this term in this form. Yeah, so it can be omega, we may know omega. And RBA is basically the vector of this one, so we can easily measure it. We can easily find it because it's the length of link is known. And if you also know the orientation of link, then this vector is known. Yeah. So you just represent VB in this new form equals VA plus omega cross RBA. So just the same thing I put here. So also relative velocity. Previously we said there's a relative position, so RB equals RA plus RBA. So we can also use a similar representation for the velocity. So VB equals VA plus VBA. So the absolute velocity of B, point B, equals absolute velocity of A plus the relative velocity between B and A. Yeah. So this is basically, you differentiate this one with time, you can get this one. And in the position, we can draw this triangle. This RA, RBA, RB, they are going to form a triangle. And same as the velocity. Based on this equation, we know this three vector is going to form a triangle or maybe a line. Yeah. So VB equals VA plus VBA. here I just randomly draw the length of VA and VB. Yeah. But no matter how the VA, how large or how small VA or VB they are, they will always form a triangle. Yeah. This just to represent their relationship. So VB equals VA plus VBA. Or sometimes you may want to represent it in a different way. You can also say VA equals VB. So in this case, VB. You can also represent in relative velocity of A to B. Yeah. Very similar to the one on the slides. But you just use different relative velocity. One is VBA, one is VAB. And just remember, because right now we are dealing with this rich body link, so the VBA can be represented as omega cross RBA. This only happens when the RBA belong to the same rich body. In another case, it may not be in this form. But right now in the following lecture, we are going to discuss this case first. So we'll just stay with this for a while. And usually when we draw, we call this it's a polygon. Right now it's a triangle, but we may have more vector later, so they may become a polygon. And we call this a velocity polygon. So this velocity polygon is helping us to know the relationship between those absolute velocity and relative velocity. And usually we just put a few labels here. So because VA is pointing from origin to A, so we will put a O, that means origin, at the origin of the arrow. And this VA is pointing from O to A. So the end of this arrow, we will label it with A. And for this one, because it's pointing from O to B, so we put a B here. And this VBA is pointing from A to B, so it will from A to B. Those labels can help us to figure out what's the direction. So similar to this one, I'll put an O here. Because these two are absolute velocities, so I want them to start from the absolute origin, which is O. And pointing to B, so I put a B here, pointing to A here. And it's VAB is the relative origin for this one is B, so it's pointing from B to A. Yeah. You may write in this form, it might be more clear for you. Any questions so far? So we are going to use a velocity polygon to help us to find the velocity, to perform velocity analysis of our desired mechanism. So here just some instruction. So I'll just read them. So we'll see an example later, so it will be more clear for you to see the example directly. But let's just go through the steps. So first, you will draw a diagram of a mechanism to scale. And you will set the origin and start from the origin at the velocity vector, which can be readily calculated, like velocity with respect to the input link. And at other velocity vector with known direction and or the amplitude. You may still be confused for now, but let's take a look over this example. I think it will be clear once you understand this example. So suppose we have a 4-bar mechanism, and we are going to use a velocity polygon to help us to find the velocity of the output or a certain point of this linkage. So usually for this analysis, we will know the input first. So in this case, the omega 2 is given. So we know the angular velocity of this input link. Then we are trying to define find VC. So we try to find the velocity of this point C. So our goal is to find VC, but we will get the omega 2 first. So as we mentioned, we will draw the velocity in scale. So currently the bar is in this angle, and we know there's a certain omega 2. So by knowing this omega 2, is there any information we can find here? Is there any absolute velocity of certain point we know already by knowing this omega 2? If we already know omega 2, then we know all the absolute value, absolute linear velocity, any point on this link. The linear velocity of any point on this link are known, right? If I know the angular velocity. Because the linear velocity is basically angular velocity times the length between the point to the origin. So I know, well, it's a bit small. So we know omega 2 here. How can we get the VA? Suppose I want to know this velocity of this point A first. Then what's the, how can we represent VA? What's the linear velocity of point A? VA is basically the radius times the angular velocity. We know the velocity of point A, we call it VA. VA is omega 2. Omega 2 is provided in the question. So we know omega 2. Omega 2 times the length of this bar. This bar, we call it, we just call it RA. Omega 2 times RA would be the value of VA. Yeah. And how about is, so by times omega 2 times R, you will get the value of this velocity. How about its direction? The omega 2 right now is counterclockwise. So we know the velocity is going to be perpendicular to this bar, right? It's just tangent to the motion of the point. So VA is perpendicular to this bar. So we know the value of VA, and we also know the direction of VA. So here I just draw this VA, just draw the VA here. And the direction must be the same as this one. Yeah. So that's and I just draw them in scale. You can define a scale by yourself. Here I just define a certain scale. I suppose VA is in this large. Yeah. So our goal is to find VC. Yeah. So we're still far away from finding VC. Yeah. So we know VA. So before we find VC, let's try to find something easier first. Let's try to find VB. Let's try to find the velocity of point B first. Then, yeah. So I just label them with the O and A. So I know this VA means from the origin pointing to the point A. Okay, so here I want to find the velocity VB first. I think it's easier because we already know one thing about VB. We don't know the omega 4 yet, so we don't know the value of VB. But right now, we know the direction of VB, right? Because we know this bar, I don't know how fast it's going to move. But I know it's moving, this point is moving in this direction because it must be perpendicular to this bar. So I know the direction of VB. I don't know the size yet, but I know the direction. So that means if I know the direction of VB, in this velocity polygon, I just erase it. Velocity polygon, we use VA, VB. VBA. Originally, I have this VA, and I want to find VB. Right now, we don't know VB, so we try to find VB. And so, if we want to graphically solve this problem, this one is different from that one, but they just example. If I try to find VB, if I know the direction of VBA and I know the direction of VB, I can draw two lines on this plot, right? Suppose I know the direction, but I don't know the length, so I just randomly draw a straight line. I don't know where is the intersection, so I just randomly draw a line. I know the direction of VB, so I just, corresponding to the direction, I just draw a line, and it's passing this origin. So I know VB is on this line, but I don't know how long it is. But I just draw it here. Somehow it's an information, but the information is not complete. But if I can somehow also find the direction of VBA, I still don't know the length of this VBA, but if I know the direction, and I just random draw the length. And the intersection of this VBA line and this VB line, there's going to be an intersection. And this intersection is going to be point B. Once I find this point, I know the value of VB. So that's what we are going to do there. If I know the direction of this one, I don't know the size. I don't know the direction of this one. Then by drawing these two lines, I can find an intersection. It's basically solving the equation, but graphically. If you find the x, maybe this line is x plus 2y equals something. This one is x minus 3y equals something. Then we solve them graphically. So back to this one. Right now we know VA. We try to find VB, but we know the direction of VB, but we don't know the value yet. But that's okay. We just I know the VB must be perpendicular to this one, this bar. So I just draw a blue line from the origin. Yeah, just be careful because the VB is passing this origin. So you must draw it from this. This blue one must be passing this origin. Okay, so I know VB is somewhere here. Yeah, the length, we don't know yet, but I know the direction, so I just draw it. But we need to find another line. We need to find the VBA. Let's see if we can find VBA. So what's the, how can we find VBA? Because VB, well, this one is a ridge body, so the length of VBA, the length of BA is not going to change. And VBA is the absolute velocity. It's not a, sorry, it's the relative velocity. So we know when we say VBA, the BA is, we consider the A as the origin. Yeah, and B, because right now it's a ridge body, so basically B is rotating about A with this radius. So if this one is the origin and we want to find the relative velocity of point B to A, then what would be the direction of VBA? So it's similar to the previous, the VA and VB. We know the VBA is going to be perpendicular to this line. Yeah, because it's B relative to A, so we consider A as the origin. So B is rotating about A. Can you accept this one? We only look at VBA. We're not looking at the absolute value. Because the meaning of VBA is B relative to A. So that means this, we just look into this triangle. So right now we are considering A as the origin. So it must be, everything is rotating about this one, it's moving corresponding to this temporary origin, A. So if we consider this one as origin, and we know this one, it's not going to be compressed or stretched. So the only movement this point B can perform is either in this direction or in this direction. We don't know yet. It may be pointing up or pointing down. Either way is possible. Yeah. But I know because this one is a ridge body, so it cannot go this way or this way. The only way it can go is this way. It's rotating about point A. So it must be perpendicular to this this AB line. So by doing so, we know the VBA, the direction of VBA. It must be perpendicular to this line. So we can just draw this line. And we know this VBA is going to pass point A and point B. And right now we only have point A, so we just let it pass point A. Yeah. But once you draw this line, then you can find intersection of this VB and this VBA line. Then the intersection is going to be point B. So by doing so, we can get, you measure the length of this OB, then this is going to be the value of the velocity of point B. Yeah. If you want to know the relative velocity between B and A, you can just measure the length of this one. Okay, so we'll continue to work on this and to find the velocity of point C next time. And so I'll see you next Monday.